All right, so you've now got your ice core, or you've got your ring core, your tree ring core, or you've got your sediment sample. How do you know what year, what time that thing actually represents? Well, that's what this video is going to talk about. It's going to talk about how we're actually able to date these samples to determine what time they represent. So just to make sure that I'm very clear, I'm not talking about this kind of dating. Nice, romantic, candlelit dinner, not that kind of dating. I'm actually talking about this kind of dating. Trying to figure out when a sample represents. What time period does it represent? Now, the good news is this is actually not super hard to do, but it's really useful for us to figure out things such as, when did the dinosaurs die? How do we know that Yellowstone erupts roughly every 700,000 years? How do we know the end of a previous era? When there's some kind of cataclysmic event, how do we know about that? And luckily, there are actually two ways that we can do this. The first is what's known as the principle of superposition. The principle of superposition. It sounds really fancy, but it's actually not that bad. The second one, you've probably heard it at some point, what is known as carbon dating, or more generally, radiometric dating. So let's talk about these. First, the principle of superposition. So earlier, I was sort of, in the previous video, I was sort of alluding to how ice cores and sediment cores form. And the way that they form is that every time a snowstorm hits a location, it dumps some fresh snow on top of what was already there. If it's an area that never thaws, if it's an area that never goes above freezing, what it's basically falling on is old snow. And so what you have is you have new snow on top of old snow. Then the next storm comes in and you get new snow on top of that. And so simply put, the newest stuff is at the top. The next newest stuff is below that, then the next below that, then the next below that, yada, 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 all the way down to the bottom is the oldest. So the newest is on the top, the oldest is on the bottom. This is actually really helpful with certain things such as ice cores in particular. The reason why is that ice cores have a nice little time step in them. Mother Nature actually does us a favor with ice cores. Tree rings work the same way. The newest ring is the outermost ring. Then the second ring is the second youngest ring. Then the ring inside that's the third youngest. And then the oldest is the one in the center. So all of that being said, the principle of superposition combined with the nice little timestamps that Mother Nature leaves us actually helps us really put together a nice little tapestry of past years. As I mentioned a moment ago, Mother Nature does something really special for us with ice cores. In places such as Vostok, Antarctica, you're going to be surprised to hear this. It may sound counterintuitive, but in places such as Vostok, Antarctica, and most polar and subpolar locations, summertime is their wettest time of year. It is the time that they get their snow. Wintertime, on the other hand, is a very dry time of year. So here's essentially what happens. Every summer, fresh snow falls. Fresh snow falls, and then winter comes. When winter comes, there's no new snowfall. However, our atmosphere is filled with trillions and trillions and trillions of microscopic particles, things like dust, sea salts, debris, anything, including things from many, many millions, or millions, many, many thousands of miles away that end up getting mixed up into the atmosphere, end up getting distributed around the world. Well, during the winter time, there's no new snow falling. However, there is some of this dust, some of this stuff in our atmosphere that ends up actually falling down and getting deposited on the top of that snow, on the top of that ice. And then the next summer, more snow comes in on top of that. Then winter comes and you get a little bit more dust. Then the next summer, more new snow on top of that. And here's ultimately what it creates. It creates this nice little dichotomy where in an ice core, the lighter colored layers, when looked at through a microscope, you can actually look at these through a microscope and detect what the colors are. The lighter colors represent summer. The darker colors represent winter. And you see these nice little banded pairs. Here's a little summer stripe, then here's a winter stripe. Well, there was summer and then there was winter. That is one full year. Then the next summer right here. Then the next winter, that is another full year. Then summer right here, winter right here, that is another full year. And so literally we can actually use these layers and just count back to previous seasons. Wow, Mother Nature wants us to know this stuff. I mean, that, to me, that is incredible that we can actually do that. Now, the bad news is for tree rings and for ice cores, tree rings represent a particular growing season. Ice cores, the light dark pair, represent a year. Sediment samples and other things usually aren't that obvious. But guess what? Mother Nature really wants us to know this stuff. And so here's what Mother Nature does for us. Every single day, when something is out in the sun, when it is exposed to any kind of sunlight, a certain amount of carbon in our bodies actually becomes isotopic. An isotope is simply an atom with more neutrons or less neutrons than it would normally have. Usually an atom will have the same number of neutrons as it has protons. That's the most chemistry oriented I really get into this class. And so what actually happens is when you're out in the sun, it makes it a little bit easier for that kind of stuff to happen, for isotopes to form. And then I hate to break it to you, you die. Everything dies. Well, when something dies, it ends up getting buried beneath the surface of the earth. It no longer has access to sunlight. And so those new isotopes aren't being generated anymore. Furthermore, the isotopes that were generated are unstable. And they actually decay at a set rate known as what's called a half-life. Basically what it is it's how long it takes for half of this isotope to decay. So here's how that works. For carbon dating, there's a certain isotope called carbon-14. It is present in all organic things. It is present in all organic things. It is produced when sunlight strikes the atmosphere. And all living things, and including some non-living things, absorb this carbon-14 into their bodies. And then they get buried. Once they get buried, they're no longer exposed to this carbon-14. Furthermore, the carbon-14 that is in their body begins to break down. What we can actually do is compare how much carbon-14 is currently in something to how much carbon-14 would still be in it if it was on the surface. And we can actually use that with our understanding of the half-life. How much carbon would there be after a certain period, and then another certain time period, and then another certain time period, to then actually give us a date. And again, when I say a date, I don't mean like April 16th, 2010. What I mean is like a really good ballpark idea. So this is 37,000 years old. This is 37,000 years old. So the way that half-lives work is simply at the surface of the Earth, an object is going to have a certain amount of carbon-14 in it. Once that thing gets big at the surface of the Earth, the carbon-14 begins to decay. After one half-life, the amount of carbon-14 that that organism, that thing still has, is now what it was when it was at the surface. Then in a second half-life, half of what was left behind is also gone, so now you only have a quarter left. Then after a third half-life, you now only have an eighth left. After a fourth half-life, you only have a 16th left. And this goes into what's called exponential decay. So first it's all of it, then it's half, then it's a fourth, then it's an eighth, then it's a 16th, then it's a 32nd, then it's a 64th. If you've ever played the game 2048, you kind of know where this is going. The number gets exponentially bigger and bigger and bigger. And we can then use how much is currently in there compared to how much would be in there at the surface to then give us a ratio, and then we can actually use that to determine, okay, this is how old this particular sample is. Now, that being said, one of the biggest downsides of carbon dating is that carbon has a relatively short half-life. A carbon-14 has a relatively short half-life. It's really only useful for looking back 30,000 years. Now, I don't know about you, 30,000 years seems like an awful long time, but unfortunately, when we want to figure out what happened to these folks behind me, 30,000 years ain't gonna cut it. So we need to actually have other isotopes that allow us to look back even further. Well, guess what? As I just said, Mother Nature loves to hook us up. So we actually have other types of isotopes that can actually help us look back even further, such as uranium-238, half-life of 500 billion years. 4.5 billion years, that is essentially the lifetime of our Earth. Uranium-235, 713 million years. Thorium-232, 13.9 billion years. That's almost the age of our entire universe. And then plutonium, 2.4 million years. So these are very, very useful for us to look back even further. And each one of these is a naturally occurring item that we can use to look back into the past. So in essence, between the principle of superposition, new layers being at the top, old layers being at the bottom, and then radiometric dating, we can actually put together a pretty good piece of when a particular sediment was, or what time a particular sediment or a particular layer represents. So now we have our date. Now we know when this particular sample represents. So we're halfway there. Next, we need to figure out, what do we actually do with that sample? How do we figure out what it's actually telling us? How do we throw it into an interrogation chair and Chuck Norris the hell out of it? But we'll talk about that in the next video. Also, sorry for this little awkward moment where I have to go and click stop. The keyboard shortcut's not working, and just a little behind the scenes production thing. But we'll jump into that. We'll jump into talking about what these things are actually telling us next time.